Ms. Woyna, you are speaking at the CADFEM conference about exporting transformer losses, distributing using PyAEDT. Could you give us some quick overview? What's the content of your presentation?
Yeah, so first of all, thank you for the invitations. It's really good to be here once again in the CADFEM conference, so thank you for that, and thank you for the invitation here. So yes, I will talk about a specific case of one of our automated workflows. So I will discuss how we streamline our product development using PyAEDT to automate the multiphysics workflows.
And what was the intention for this one? When started, what's the important point to do this?
Yeah, so important point, of course, in general in our transformer product development is to streamline the whole process, also stick of course to the customer requirements, and all at the lowest possible cost and also in timely manner. So these are like the motivations why we do this. And one of the key aspects here is the thermal management of transformers, and this is what I will today talk about.
So it is something which is repeatedly done with different designs.
Exactly. This is for each and every transformer we ever designed. This is like the one of the key points. Yeah. And
what are the core tools or simulation parts which have to be done for such a multiphysics analysis? Yeah,
this is a good question. So I'm electrical engineer, so I see everything around electromagnetism and electrical engineering, but sure, we need to start from the electromagnetic simulation to, in this case, when I talk about thermal management, we calculate the loss distribution. Sometimes in 2D is enough, sometimes in 3D, but anyway, we need the loss distribution, considering all the possible effects like skin effect, proximity effect, different geometries, different materials, different load conditions, and so on and so forth. So we start from electromagnetic simulation. Then for the thermal simulation, we have some in-house analytical tools, which are often implemented in MATLAB. We sometimes also, today will talk about the 2D CFD simulation. So these are now examples for the thermal management. But then, of course, we are interested in structural integrity of our transformers, and in that case, we again calculate the electromagnetic forces caused by magnetic fields and currents and their interactions. We calculate the force distribution, which we will then further use in structural simulations.
And which role plays the PyAEDT, or in general the Python axis? So if I think on a multiphysics workflow, I think on the workbench and connecting the different parts, but what's the specific of the PyAEDT?
The thing is that we want to control the workflow, the whole simulation workflow. And by the way, not only simulation, we also have sometimes some analytical, let's say, blocks in our workflow, and we also have results, often some test results.
Okay.
So the point is that we want to control the whole simulation workflow from Python. We don't want to give Workbench the control or anything else. We want to have a Python script which controls the whole workflow, includes all these blocks, whatever they are, mostly simulation, but also other blocks. So this is the thing, and PyAEDT is really the enabler for all this.
So there was 2 points which I found very interesting. So first, there is also measurement data which comes into the simulation, into the workflow.
Yeah.
So there are material data, or is it really something measurement on the tool?
Yeah, so it depends a bit on the transformer and depends on the customer requirements, but there is a certain standard set of tests that have to be performed for each transformer. This includes like DC loss, AC loss, short circuit impedance, resistance, also in some cases also heat run test where the temperature rise is measured. So these are things that exist for each and every transformer, and because we have designed over the years obviously quite many transformers, this way we can also validate our new workflows against existing designs and the measurements.
Okay, so also the evaluating between simulations, calculations and measurements.
Yes, exactly. This is also an important point that we sometimes need to calibrate something. We see some tendencies that simulations predict higher losses so we can calibrate them, things like that.
So when I hear Python programming, so I have to think back to my study time when I had these courses. Is it really something you have to be expert in programming, or how you can use this Python?
Yeah, this is a very good question. I'm an electrical engineer. In the university I had to learn the basics of programming, but that's it. So I'm not a professional programmer, and I think this applies to almost every attendee of this conference. And this is exactly the strength of PyAEDT. You don't have to be a super expert to use PyAEDT and to automate your workflows. Yes, you need to learn a couple of things, but professional programmer, that is not needed.
So you don't have to be afraid about the Python?
No, definitely not. And I mean, this is the reason why Python is actually currently, I think, the most used programming language, because it's easy.
Yeah, when we talk about automatization, so there is a lot of effort to first make the automatization, but how you see the advantage then when it's running, when it's in use?
Yeah, this is a good point. So I always think about it like that, and I have also first-hand experience of that. So if you give a transformer design for 5 engineers, and then you repeat the exercise, same design, same engineers in 2 years, in the end you will have 10 different sets of results, and what is now right and what is wrong. So this is something like a human factor. Yeah. It is there, no matter want it or not, but it's there. So this is one very important advantage of using PyAEDT, so that these human errors can be minimized. So what we can do, we can take all these 5 engineers, discuss, combine the best practices, and plug all these 5 best practices in one automated workflow.
So that means if I have the automated workflow, it's following always the same steps, the same rules. Everyone, or the program, use the same rules all the time. There's no different participants in this one, and that makes the automatization. Okay, so maybe come to another point. So you have now, or you're working on this workflow for the transformer or for some specific application. Do you think there's other applications in your company or in general where this multiphysics workflow, including PyAEDT, is important?
Oh yes, I could give a long list of especially ideas, but if I start like from priorities, so one thing is this electrothermal workflow, which is, I would say, the highest priority. But then we also have to consider the structural integrity of the transformers. And this is very important, and in this case we do electromagnetic simulation with Maxwell and couple it with structural simulation to see if transformer, for example, withstands short circuit forces. So this is one example. Another example could be NVH, or noise, vibration and harshness. This is also important, especially for distribution transformers, because they tend to be placed near where people live. They have to be relatively silent. So these are a few examples. Then maybe not exactly multiphysics, but more like a system or circuit simulation. This is also something that we calculate the RLC parameters of transformer, for example, capacitances and between the winding turns, and then we use those parameters in a circuit simulation. So this is another, not exactly multiphysics, but let's say more system simulation.
That's what the electrical engineer works with, the circuits, with SPICE models or something like this, including in the simulations.
Yeah.
And where is the connections to the PyAEDT? So it automatically transfer the data, starting the simulations. That's the strength.
Yeah, so this workflow is still more like an idea. It's not really, the implementation is not there yet, but we are thinking about the possibility to calculate these RLC parameters using PyAEDT and Maxwell, and then possibly use some kind of maybe open source circuit simulator like LT-SPICE, because also such a library exists called PyLT-SPICE. So this is one possibility, that we make PyAEDT talk with PyLT-SPICE and have a nice workflow. But this is only an idea, so we will see where it goes.
I found this very interesting, because I think that's the point, the connection between the electrical engineer and the person who does the simulation, three-field simulations. It's sometimes a little bit difficult to connect them to. Okay, let's talk about a little bit about the value. So if you make such a workflow, or the company decided to go into these directions, there must be some reasons, there must be some value behind it. What's the big advantage of this one?
Yeah, this is of course very relevant question. So I mean, how I see transformers is like 150-year-old technology. Almost every school kid knows how transformer works, and one could ask, okay, why all this? Why do we have like an army of R&D engineers thinking about this? But I think here Pareto principle applies. So when we, let's say, approach the 99% of all the design work, it gets harder and harder. So we are maybe there at this last 1% to try to optimize really the performance of our transformers. And there we need to, turn every stone and look everywhere. How can we streamline and how can we really optimize everything?
So we come closer to the limit, of the physical limit, and we have to look into more details, and that's the challenging part. And that has also value for the company. So it's 99.6 or 99.7 efficiency makes a big difference.
Exactly, and if we can make our transformer a bit cheaper, a bit lighter, this is of course a huge value then.
And that's where the part multiphysics and that optimization plays an important role.
Exactly.
Okay, so what do you think it's next to your work? So you're presenting today, as I understand it was the starting point of multiphysics using PyAEDT. What will be the next steps?
Yeah, in that particular workflow I'm going to talk about today, which is electrothermal simulation. In that one we are considering only the winding losses, which are the, let's say, the dominant loss component in transformer. But we also may need to look into other loss components, for example, core losses or losses in some structural parts or things like that. That is like the immediate next step. But then I think looking a bit further, we are really interested in automating also these electromagnetic structural workflows. Also, an important thing is that currently many of these workflows work locally. So I have them on my laptop and I can run the simulation on my local, for example, Maxwell installation. But what we try to do in the future is to containerize these workflows so that a user only have an interface to this workflow, clicks a button, and user doesn't have to care where the simulation runs, if it is cloud resource, virtual machines, whatever, and if the licenses are available or not. This is something that users shouldn't think about. So this is a next step what we also are thinking about.
So we might see at the next CADFEM conference
a
new update on the presentation and also include other losses than only the winding losses in the simulations and more automatization.
Hope so, yeah. Looking forward to that.
We are too. We're looking forward for these presentations, and thank you for this interview.
Yeah, thank you.
Thank you.